Assalamu alaikum everyone. So today we are going to start the AS paper. It's 9701 AS Chemistry paper 22 and it's May-June 2024. Okay. Now question number 1. They are asking for one minute, please. Okay, thank you, Arpa. Okay. So complete table 1.1 using relevant information from the periodic table. Okay. So if you see over here, you are provided with the two elements and their nucleon numbers are mentioned, but their proton numbers or atomic numbers are not mentioned. So you can find them in the periodic table. So this is magnesium and aluminium. So the atomic number of magnesium is 12 and the atomic number of aluminium is 13, right? So the atomic number is the proton number. So it is going to be 12 and it is going to be 13 and they are asking for the number of electron. So the number of electron are identified by the charge. If the atom has a positive charge, so the number of electrons are lesser and the value of the charge shows how many electrons are lesser, right? So in case of magnesium, it is going to be 12 minus 2, which is going to be 10. So 10 electrons over here. And in case of aluminium, it is going to be 13 minus 3. So it is going to be 10 again. So we got the number of electrons, right? Okay. Now, next part. State and explain the difference in the ionic radius of aluminium and magnesium. So if you see, if we talk about magnesium, magnesium has a positive 12. So there are 12 protons in the nucleus, and these 12 protons are attracting the 10 electrons. So for example, if its size is going to be like this. So if you look at aluminum, aluminum has 13 electrons. So 2 and 8, right? So there are going to be two shells around aluminum and the two shells are going to be around magnesium and around aluminum. But aluminum has 10 electrons. The number of electrons are same, but the protons are greater. The aluminum has 13 protons, so it is going to attract the 10 electrons with the more force. So as a result, the size of the aluminum ion goes smaller than the magnesium ion. Is this understandable? Okay. So we are going to state the first the difference in the ionic radius. So we will write that the aluminum ion is smaller than magnesium ion. As both have same number of electrons and same shielding as well, right? But the nuclear charge of aluminum ion is greater, hence stronger nuclear forces of attraction in aluminium as compared to magnesium ion. Is this clear? Okay. Now next part. Draw a label diagram to show the structure and bonding in sodium. So if you look at sodium, it's a metal, right? So in metals, what we are going to do, we are going to make the cations, right? And a uniform structure of a cations. And in the spaces between them, we are going to draw the delocalized electrons, right? Then you are going to label it cation or positively charged ion and label this negatively charged as delocalized electron. Now, next part. Figure 1.1 shows the variation in the melting point of period 3 elements. Okay, 1 minute. Yeah, period 3 elements in their standard states at room temperature and pressure. Okay, so if you see, they have given you the melting point until the silicon. Explain why silicon has a high melting point. So if we think of silicon, we know that silicon is a giant covalent structure and there are strong covalent bonds throughout the structure. So large amount of energy is needed to break those strong covalent bonds throughout the structure. So silicon is giant covalent lattice having strong covalent bonds throughout the structure. Hence, large amount of energy is needed to break these bonds. Is it clear to all of you? Now, next part, complete figure 1.1 to show the variation in the melting point of phosphorus, sulfur, and chlorine. So if you look for phosphorus, phosphorus is P4. These three are simple molecular, right? Sulfur is S8 and chlorine is Cl2, diatomic. So phosphorus is P4, sulfur is S8, and chlorine is Cl2, right? So what is going to happen that as these are simple molecular and their melting point depends upon the strength of the intermolecular forces which are very weak. So that's why the melting point decreases and phosphorus has a very low melting point. Then sulfur is octatomic, has more electrons. So if it has a more electrons, so its intermolecular forces are going to be stronger than the phosphorus, sorry. And then chlorine is just two atoms molecule, diatomic molecule. So its intermolecular forces are weakest. So the melting point is going to be the lowest. Is this clear to all of you? So this is how you can draw the curve and make sure whether it's a phosphorus or sulfur, their melting point stays lower than that of sodium. Okay. Now, two period 3 elements react with an excess of oxygen at room temperature. Okay. Complete table 1.1, 1.2. Okay. So period 3 element is sodium, state of oxide at room temperature. Okay. For both sodium and sulfur, approximate pH of a solution made when the oxide is added to a water. Okay. So for sodium, as sodium oxide is an ionic compound, so its state is going to be a solid. And if sulfur, it's a sulfur dioxide, then non-metal oxides are usually gases, except for phosphorus oxide. So it is going to be a gas. Then pH. So sodium oxide, when dissolves in water, it forms an alkali, and sodium hydroxide is a strong alkali. So you can write the pH 14 or 12 or 13. And sulfur dioxide is formed, which is then dissolved in water to form sulfurous acid. So its pH is around going to be 1 or 2. Okay. Now, the solution made in column 3 of table 1.2 are mixed together. Name the type of reaction. So we know that the oxides, one is an acidic oxide and the other one is a basic oxide. So when the acid and base reacts, the reaction is called neutralization. Then write an equation to describe the reaction between phosphorus oxide and excess of water. So remember, when a non-metal oxide dissolves in water, it forms acid. So when P4O10 dissolves in water, it reacts with water, hydrolyzed and dissolves to form phosphoric acid, which is H3PO4. To balance the equation, you need to put 4 over here. And as you put the 4 over here, there are 12 hydrogens on the left side, on the right side. So we are going to put 6 before water to balance the hydrogens on both the sides. Oxygen already get balanced. Is this clear to all of you? Now, next, aluminum hydroxide is an amphoteric. Explain what is meant by the amphoteric. So amphoteric is the one which reacts with, which should, either way you can write, which shows both the acidic and basic characteristics, or which can react with both acids and bases. It can be considered correct. A substance which reacts with acids and bases both. Now, next part, write an equation to describe a reaction that occurs when aluminum hydroxide reacts with sodium hydroxide. So, aluminum hydroxide is an amphoteric oxide, right? And it is reacting with sodium hydroxide, which is an alkali. So, over here, the behavior of the aluminum hydroxide is going to be acidic. Yes, sir, and we are going to just join them. So when the sodium and aluminum both are there, so what is their charge? It's +1 and it's +3. So the overall charge becomes +4, and hydroxide is -1. So you are going to put 4 OH, making it uh, making a salt. Is this clear to all of you? Now, question number 2. Separate samples of sodium carbonate and sodium hydrogen carbonate reacts with hydrochloric acid to produce same product as shown in table 2.1. So in table 2.1, you have the equations and their enthalpy change values, right? Okay. Complete the reaction pathway diagram in figure 2.1 for reaction 2. So if you see, the reaction 2 is endothermic reaction. So for an endothermic reaction, okay. Label a diagram to show the enthalpy change delta H2 and activation energy EA. So we have to show these two. And as it's an endothermic reaction, so in endothermic reaction, the energy of the product is always greater than the reactant. And then we are going to make one arc from the reactant till product like this. And then from the level of the reactant till the highest point, that is your activation energy. And from the reactants till the product, that is enthalpy change. And over here, we are going to mention the products that there is sodium chloride, there is a water, there is a carbon dioxide, right? And that is labeled as delta H. Okay. Now, The value for the the value for the enthalpy change of reaction 1 delta H1 is determined by the experiment using the following method. 50 centimeter cube of 2 mole per dm cube hydrochloric acid is added to a polystyrene cup. The initial temperature is recorded, which is 19.6. 0.04 moles of sodium carbonate is added to the mixture, and the mixture is stirred. All the solid sodium carbonate disappear and a colorless solution is produced. So see, here you got the hint. If they are saying that all the sodium carbonate disappears, so it is the limiting reactant, right? It is completely being used up. So it clearly hinting you that this acid is in excess. Okay. The maximum temperature recorded during the reaction is 26.2 degrees Celsius. Describe one other observation that shows the reaction is complete. So it's a reaction with the sodium carbonate. So when they are reacting, beside the disappearance of a solid, what we are going to observe, we are observing the fizzing or the bubbling of the solution, bubbling in the solution as the carbon dioxide is made. So that bubbling stops or the effervescence stops, right? So effervescence stops. Is this clear? Now, in the next part, calculate the value for the delta H1 in kilojoule per mole. Assume the specific heat capacity for the reaction mixture is same for water and no heat is lost to the surrounding. Show your working. Okay. So for the specific heat capacity, if you remember, that's fine. It's 4.18. And if you don't remember, just look at the page before the periodic table. Over here, they have given you the specific heat capacity of water, that is 4.18. Okay. So if you recall the enthalpy change formula, that is minus mc delta T over n times 1000. So minus the whole mass of the solution is 50 centimeter cube, and it's for aqueous solution, remember, 1 centimeter cube is 1 gram. So if 50 centimeter cube is the solution, whole solution, so it is 50 grams. Okay. That is for aqueous solutions. If they haven't given you anything, just given the volume of the aqueous solution, so you relate like this. So the mass is going to be 50. The specific heat capacity we have seen from the back, it is 4.18. Now, the change in temperature. So it's 26.2 and 19.6. So 26.2 and 19.6. So 5. Is it 7.6? Yes, can anyone confirm me quickly? It's a positive, right? Then divide by number of moles. So if you see the equation, that is the reaction of sodium carbonate. So the ratio between sodium carbonate and water is 1:1, right? So if we have used 0.04 moles of sodium carbonate, so the moles of water formed are 0.04 carbon as well. So do remember, whenever you are calculating for the reaction of the acid and an alkali forming water, so you are going to put the moles of water which have been formed. So it is 0.04 times 1000. Can anyone calculate it and tell me the value, please? Yes, please do it quickly and tell me the answer.
Sir, is it negative 39.71?
Yeah, you can do like that as well, Arba. You can just put the negative sign at the end. No, I think you did the mistake in putting the values. See, we have uh, 50 times 4.18, that is
Yes, sir,
209,
it is
times
39.71.
7.6. Okay, is this value is correct? I don't know. Did I calculated
Yes,
the
sir. Sir, it
this?
is, I think it is 6.6.
Yeah, see, 6.6. Okay. So
Yes.
that's what I was asking. So it is 6.6, right? Okay. So now 50 times, now calculate
Answer
it
is,
in
answer is minus 34.485.
minus 34.485. So if you are going to put it in the three significant figures, it is going to be minus 34.5. Okay. Now, next part. The thermal decomposition occur when sodium hydrogen carbonate is heated. This is a reaction 3 and they have given you the equation. Calculate the enthalpy change for the reaction 3 delta HR using the data in table 2.1 and the value of delta H1 calculated in V2. Okay. So if you see, we have to calculate the enthalpy change for this reaction. And in this reaction, we have both sodium carbonate and sodium hydrogen carbonate, right? Okay. Now think, if you react this sodium hydrogen carbonate with acid, what we are going to get? We are going to get 2 moles of sodium chloride plus water plus carbon dioxide, isn't it? So 2 moles of water and 2 moles of carbon dioxide. So if we react this one with the water with the acid, we will going to get the same products. So that is delta HR, which we need to calculate. On the left side, it is twice of sodium hydrogen carbonate. And for sodium hydrogen carbonate with HCl, we got this value. And it is when 1 mole of sodium hydrogen carbonate is being reacted. And over here, it's 2 moles are being reacted. So it is going to be twice of positive 27.2. On the right side, it's the reaction of sodium carbonate with hydrochloric acid when we have calculated its value. So it is going to be minus 34.5. Now, if you see the roots, so the left side is the direct root and the right side and the middle delta HR are the indirect roots. So the equation initially becomes twice of positive 27.2 is equals to delta HR plus minus 34.5. See, this is directly converting into this and this is going this and this. So we are going to add these two and these two are is equals to this one. So that's how we make the expression. So the delta HR is equals to 2 times 27.2 minus
Negative
minus
88.9.
34.5.
Positive. Okay. Sir, won't there be a minus sign also on minus 2 into 27.2?
No, we just move
Okay.
this one over here. Can you
Oh,
calculate
yes.
again?
88.9. 88.9.
No, I think your answer is not correct. Yeah, 88.9. Okay, that's fine. So, and it's a positive, right? So positive 88.9. Is this clear to all of you? Now, C part. Z is a salt that contains a period 4 element from group 2. Okay. When Z is heated, a brown gas forms. Identify the formula of Z. Use it to write an equation for the reaction. So period 4 and group 2. Period 4 and group 2. So this is group 2 and this is 1, 2, 3, 4. Period 4. So it is going to be the calcium and the brown gas is forming. So it means brown gas is formed when nitrogen dioxide gas is released. So it means it's a calcium nitrate. On heating calcium nitrate, we get the nitrogen dioxide gas. So calcium nitrate on heating gives you calcium oxide plus nitrogen dioxide and oxygen. To balance this equation, we need to put 2 over here and half over here. The equation is balanced. Is this clear to all of you? Okay. Now, okay, let's move to the question number 3. Describe what is meant by the dynamic equilibrium. So we know that, and it's for 2 marks. So we are going to write 2 uh, things. First, that we know that rate of forward and backward reaction gets equal. And secondly, the concentrations of reactants and products are constant. It means they are not changing any. Now, next part, reaction 4 describes the reversible reaction between yellow iron to iron 3 ions and a colorless cyanide, thiocyanide ion to produce red FeSCN2 positive. Okay. So we have iron 3 positive having a yellow color, and when it combines with SCN, the new complex ion is formed with the red color. An equilibrium mixture contains aqueous iron 3 positive ions and cyanide ions and FeSCN2 positive ions. A few colorless crystals of soluble KSCN are added. The mixture is then left until it reaches equilibrium again. The temperature of the both equilibrium mixture is the same. Reduce the change that occur, if any, in the equilibrium mixture after KSCN is added compared to the original mixture, equilibrium mixture. Okay, so if you are adding KSCN and it's a soluble, so it is going to be ionized into K positive and SCN negative. So there are more amount of SCN negative. And if there is a more amount of SCN negative, so the equilibrium shifts towards the right, more of this complex ion would form, and as a result, the solution becomes more red, right? Now, change in the relative concentration of Fe3 positive. So as we have decided that the equilibrium shifts over there, so the concentration of Fe3 positive decreases. Next, change in the value of equilibrium constant Kc. So see over here, the temperature of both the equilibrium mixture is the same. So if the temperature is same, remember Kc doesn't change. No change. Kc stays constant. It only gets changed. Kc or Kp only gets changed when there is a change in temperature. Otherwise, it stays the same. Now, okay. Next part. The expression for the equilibrium constant Kc for reaction 4 is shown. 5 exponent minus 5 moles of Fe3 positive, 5 exponent minus 5 moles of thiocyanide are added together and allowed to reach equilibrium. The total volume of the mixture is 25 centimeter cube. At equilibrium, the concentration of SCN is 4.23 exponent minus 4. Calculate the Kc expression. So at equilibrium, we know the concentration of one reactant only, and we don't know the concentration of the rest of them. So we are going to make the ice table. So our equation is this. Fe3 positive is reacting with thiocyanide ions, forming iron thiocyanide 2 positive, right? Go with the ice. So it is 5.00 exponent minus 5. It is also 5.00 exponent minus 5. And it is 0.00 because we haven't added this one. At equilibrium, it's 4.23 exponent minus 4. So it means this must be the change, this much amount of 4.23 exponent minus 4 is formed. Now, if you see the mole ratio is 1:1, so it means exactly this number of moles are going to be released, are going to be used up. Right? Oh, okay. So see, this is a mole per dm cube. So you can do two things, either convert this into concentration and then put it over here, or convert this into the moles and then put it over here. Okay, so it's easy to do the concentration. So the total volume is 25 centimeter cube. So the concentration is going to be 5.00 exponent minus 5 over 0.025. Can anybody tell me the concentration, please? Yes. Yes, can anyone tell me the concentration?
So it's 2 to the power minus 3.
2 raised to the power minus 3, which means 0.002. Right? Okay. So these are the initial concentrations. 2.00 exponent minus 3. 2.00 exponent minus 3. And the change is exactly the same as FeSCN, but it's in negative because these are being used up. So minus 4.23 exponent minus 4 for both of them. If you subtract, you will get the concentrations of both the ions at equilibrium. So can anyone subtract and tell me the value? Yes, please.
Sir, can you
Sir,
please
for
explain
Fe,
again?
See what we did. If you see, this is the concentration and these are the moles, right? So what we did, the total volume is given. So we divide the mole with the volume in dm cube to get the concentration. Is this clear? So we got the concentration of these two. We haven't added this one. So this is 0 initially. And at equilibrium, we know its concentration, which is this one. So it means exactly this much moles per dm cube has been formed. So if you see, the ratio is 1:1. So if these mole, this much concentration of this is formed, so this much concentration of these two reactants are going to be decreased or going to be used up. Is this clear? Yes, Arba?
Yes, sir. Yes, sir. Thank you.
Okay. Now, yes. Can anybody subtract the values and tell me the answer?
Sir, for Fe, it's 1.577 power minus 3.
1.577 exponent minus 3. So that is going to be the for SCN as well, right?
Yes.
Okay. So if you go for a Kc expression, so the Kc expression is going to be concentration of the product over product concentration of the reactants, right? And we take the product of the concentrations if there are more than one. So we are going to just put the values 4.23 exponent minus 4 divided by 1.577 exponent minus 3 times 1.577 exponent minus 3. Yes, can anyone calculate it and tell me the answer for units? In the denominator, we have a mole per dm cube. In the numerator and in the denominator, we have 2 mole per dm cubes. So 1 mole per dm cube is going to be cancelled out. 1 is left. When we move it to the numerator, it will become mole inverse dm cube. So that is the unit. Mole inverse
One,
dm cube. Yes, what is the
sir,
Kc value?
sir, answer is 170.089.
170.089. So 3 significant figures is going to be 170. Okay, I hope it's clear to all of you. Okay, now determine the full electronic configuration of Fe3 positive. So if you look in the periodic table, you will find Fe, the atomic number is 26 and it is a 3 positive charge, which means it has 23 electrons now. Remember the first 2 electrons always removed from 4s. So if we start, it is going to be 1s2, 2s2, 2p6. 10 electrons are being added, 3s2, 3p6, 18 electrons are being added. Now the next 2, 4s goes to the 4s, but now there is no 4s and 3d. So how many electrons are left? 5. So 3d5. We just exclude 4s because it's an ion. So the electrons are not going to be present in 4s. Okay. Now, SCN negative is a colorless. Complete dot and cross diagram in figure 3.1 to show the arrangement of the outer electrons in the SCN negative. Okay, it has a negative charge. Okay, first look at a carbon and nitrogen. We know that what nitrogen do? Sulfur usually form 2 bonds, right? Carbon forms 4 bonds and nitrogen form 3 bonds. So, as nitrogen has 5 electrons in its valence shell, and out of those 5 electrons, it shared its 3 electron, and there is a 1 pair. So carbon in return shared its 3 electrons over here, completing the octet. So it means carbon is going to share its 1 electron with the sulfur, and sulfur is going to share its 1 electron with the carbon. So the octet of carbon and nitrogen is completed off. Sulfur is in group 6. It has a 6 valence electron out of 6. 1 is shared. So 5 are left. So you are going to make 2 pairs and 1 unpaired electron, but there is a negative charge, which shows that the compound has this ion has a 1 extra electron. So you are going to show that extra electron over here with the sulfur. Is this clear? Okay. Now, question number 4. CH3, CH2, 5CH, CH3 exists as a pair of stereoisomers. Draw the 3-dimensional structure of the 2 stereoisomers of CH3, CH2, 5CH, CH3. So see this CH, this C is basically the one. Okay. R can be used to represent this whole thing. So this C is the chiral carbon. So what you are going to do, you are going to do this and just make its mirror image. Okay. Now, as they have told you that this whole thing is going to be represented by R. So just if you are putting the R over here, put R over here. Now, this carbon is bonded to a hydrogen. If you are putting the hydrogen away from the plane over here, so put the hydrogen away from the plane over here as well. Now you are left with bromine. So if you are putting the bromine over here, so just put the bromine over here, CH3 over here. So CH3 over here. So see, that's how you got the two mirror images. Is this clear? Non-superimposable mirror images. Okay. Now, a sample of this reacts with sodium hydroxide to make this. Okay, so see the bromine is removed and hydroxide displaced it. In an SN1 mechanism, SN1 mechanism is the one in which the carbocation is formed, if you remember. SN2 is the one which has both the nucleophile and the compound in the same state, forming the transition state. Complete figure 4.1 to show the mechanism for the reaction of this and NaOH include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Okay, so as it's a SN1 mechanism, so what is going to happen? This is, you are going to show a dipole, and after that dipole, you are going to make this arrow over here. So as a result, bromide gets separated. Okay, bromide gets separated. This carbon brought a positive charge. It has a H, it has a CH3, and it has a CH2, 5CH3. Now, you can see there is a hydroxide ion. So you just show the hydroxide ion with the one lone pair. And from the lone pair, make the curly arrow pointing towards the carbon, showing your product is formed. So that is how you show the mechanism of SN1. Now, let's move to the part C. Separate samples of this. Okay, halogenoalkane, right? Alcohol. And if you see, this is an alkene. They haven't shown you, but it's CH and CH2, which makes it is actually CH with a double bond CH2. Okay, so that is an alkene, that is an alcohol, and that is an haloalkane. Bromine in the dark. So bromine in the dark only reacts with alkene, right? If no reaction occur, complete table 4.1. If no reaction occur, write X in the relevant box. Okay. And otherwise, what you need to do, you need to put the observations. So bromine, no reaction over here. And from over here, it goes from orange to colorless because with alkene it reacts in the dark. PCl5. So remember, PCl5 doesn't react with the alkene, but it displaces the OH. So it do reacts with the alcohol. So as alcohol, the chlorine gets substituted. Beside this, HCl is formed, and due to the Cl, we are going to get the steamy or misty fumes. Then silver nitrate. So silver nitrate doesn't react with an alcohol. The silver actually bonds with the halide ions to give you the precipitate. So over here, there is a bromine. So you are going to get clean precipitates over here. Is this clear to all of you? Now, part B. This is heated with D to produce three different molecules, E, F, and G. So it means that it is an elimination reaction, and elimination reaction, the D with which it is heated, it is NaOH in ethanol. Name the type of reaction. So we have already identified that it is a elimination reaction, right? Now, secondly, identify D and the conditions used. So D is sodium hydroxide and the condition is in ethanol. Now, both sigma and pi bonds are present in the molecule of E. Okay. As a result of different types of hybridization in the carbon atom. Complete table 4.2 to show the number of carbon atoms with each type of hybridization in the molecule of E. Okay. For sp hybridization, a carbon atom needs to make two pi bonds. So there is no carbon atom forming two pi bonds, so it is going to be 0. sp2 hybridizes the carbon atom which is forming one pi bond, right? So this one and this one, they both are forming one pi bond. So there are two sp2 hybridized carbon. And sp3 is the one carbon atoms which doesn't form any pi bond. So if you see 1, 2, 3, 4, 5, 6. So 6 carbons are the sp3 hybridized carbons because they are not forming any pi bond. Is this clear to all of you? Describe the essential feature of an unbranched hydrocarbon that causes its molecule to show stereoisomerism. Explain how this feature leads to stereoisomerism. Okay. So first thing, I pi bond, or you can write carbon-carbon double bond, due to which rotation is restricted, right? Now across this, there is no rotation. And further, each double bonded carbon must be bonded to two different groups further. Is this clear to all of you? Now, compound W has molecular formula C4H10O. It contains only one functional group. Table 5.1 shows the two peaks with the greatest mass over charge ratio. Okay, so they have given you the molecular formula in the mass spectrum of W. Okay, if you see it's C4H10O, so isn't it? It's CnH2n plus 2O, which means that it might has a hydroxyl group alcohol. Okay. So if it is a M peak, so this one is going to be the M plus 1 peak because it has a one mass greater than that. Okay. Now what they are asking, calculate the relative abundance of X, the peak at mass over charge ratio 75 using the information from the table 5.1. So if you recall the formula is number of carbon atoms is equals to 100 upon 1.1 multiplied by abundance of M plus 1 peak over abundance of M peak. So the number of carbon atoms we know are 4. 100 upon 1.1, the abundance of M plus 1 peak is going to be X and the abundance of M peak is 50, right? So X is going to be equal to 4 times 1.1 times 50 over 100. Can anyone calculate it and tell me the value, please? Yes, please calculate it and tell me the value.
Search 2.2.
It's 2.2. So see, we got the abundance of the m+1 peak, that is 2.2. I hope it's understandable to all of you. Now, next part. Mass spectrum of W also shows peaks at mass 29 and M 39, suggest the molecular formula of these fragments. So let's see how many carbon we have. We have 4 carbons, right? So it is CH3, CH2. We don't know. We are just assuming that it's like this. So if you see it's 15 and that is 14, that is 14, that is 14, and that is 17. So 15 plus 14 gives you 29. So it is going to be C2H5, right? So C2H5 has a mass of 29. So it means that is due to the C2H5 positive charge ion. Is this understandable to all of you? Okay. Then 14 and 14 are 28. Okay. So 28 plus 17, 38, 35, right? And 35 plus 14, 49. Isn't
Sir,
it 59?
14 plus, sir, 14 plus 14 plus 17 is 45.
Okay, 45. Yeah, 45. 45 and 14 is 59, right?
59.
So see, it means this thing is giving us this. So if I go for it, so it has how many carbons? 3 carbons. How many hydrogens? 6 plus 1, 7 hydrogens and 1 oxygen. So it is going to be C3H7O positive. Is this clear?
Yes, sir.
Okay. Now, a sample of WC4H10O is heated under reflux with an excess of potassium dichromate until there is no further reaction. Only one organic product X is present in the mixture at the end of the reaction. Okay. So it means that the product is either going to be a ketone or acid, right? Because if it's a primary alcohol, it is going to form a carboxylic acid, and if it's a secondary alcohol, it is going to form a ketone, right? Figure 5.1 shows the infrared spectrum of W. Just give me a minute, please. Okay. So this is the spectrum of W, right? Okay. And see, this is the peak. This is a distinguishing peak. So from this peak, isn't it, you can conclude that the W has a OH. That is a hydroxyl OH of a alcohol, right? Because it's from ranges from 3200 to 3500. One minute, my screen got stuck. Let me reshare it. Okay. Now, figure 5.1 shows the infrared spectrum of X. So X is the product which we have identified that it is either, initially what we have decided, it is either ketone or a carboxylic acid, right? So now, if you see over here, the carboxylic acid OH is going to show you the broad peak at 2500 to 3000, and which is missing over here. This peak of carboxylic acid would be like this, if you remember. So that is missing over here, but see, this is a very important peak of carbonyl or carboxyl from 1670 to 1740, which you are showing seen over here. So it helps us to figure out that the X is a ketone. Is this clear to all of you? Now what they are saying, absorption A is shown in figure 5.1, absorption B is shown in figure 5.2. Complete table 5.3 using the information in figure 5.1, figure 5.2, and table 5.2 that is over here. Absorption A. So what we have identified that it is a OH of hydroxyl, right? And B is a carbonyl. So OH and which OH? Hydroxyl OH. And that is a C double bond O carbonyl ketone, right? Okay. Now, what they are asking next, use the information in A and B1. Okay, so that is a B1 and A, then that is this one. Okay. From A, we got its MR, that is 74. Okay. Draw the structure of X in the box in figure 5.3. So as we have already identified, it's a ketone and having a 4 carbon atoms. So isn't it? It's going to be 1, 2, 3, 4. And over here a double bond CH3, CH3, and CH2. Is this clear to all of you?
Yes, sir.
Okay. Now, why is a structural isomer of W? Okay. Both W and Y produces colorless bubbles when sodium is added to them. So it means both are alcohol. Y does not react with acidified dichromate. So it means it's a tertiary one because tertiary doesn't oxidize, right? It's a tertiary alcohol. Y does not react with warm aqueous alkaline iodine. So it's a tertiary alcohol. So it means it doesn't have CH3CHOH. This is not present. Name the functional group of present in Y. So it's again hydroxyl, right? Hydroxyl group, the OH of alcohol is present. Complete the equation. Okay. So when it reacts with N, it is going to be, the H is replaced. So C4H9O negative Na positive and H2. So what you can do if you put 1 and 1 over here, so you just need to put half over here to balance the equation. Otherwise, you are going to, or you are going to put 2, 2, 2, and then 1 over here. Is this clear? So that's how we balance the equations. Now, draw the structure of Y. So Y, we have already identified that it's a tertiary alcohol. So the carbon having an OH is bonded to 3 carbon chains. So in total, the molecular formula of Y is C4H10O. So 1 carbon is there. So the second carbon is CH3. Third carbon is going to be CH3. And the fourth carbon is also going to be CH3. So that will be the structure of Y. Is this clear to all of you? So over here, we are done with the paper. And now, inshallah, in the next class, we are going to do the February, March 2025 tomorrow. So see you everyone at tomorrow. Okay, take care. Goodbye and Allah Hafiz.